Welcome to Chem Help ASAP. In this video, we'll perform an interesting Diels-Alder cycloaddition between cycloheptatriene and maleic anhydride. We will introduce the idea of fluctional molecules, talk about the reaction, perform the experiment, isolate the crude product, and characterize the final material. Handouts for the lab procedure and NMR spectra are available through links in the video description. Before talking about the reaction, we need to discuss cycloheptatriene, or more formally, 1,3,5-cycloheptatriene. Cycloheptatriene, as we would normally draw it, is shown as form A to the left. This molecule, however, exists in an equilibrium with form B, which has a cyclohexadiene fused to a cyclopropane ring. Because of this equilibrium, cycloheptatriene is said to be a fluctional molecule. This is an example of valence isomerism, which is a fairly uncommon form of isomerism, but is encountered on occasion. The citation from Chem ed in the lower right corner provides a few paragraphs on the ideas of fluctional molecules and valence isomerism. Note that the equilibrium very strongly favors form A, so most people ignore the presence of form B when discussing cycloheptatriene. Form B, however, is distinctive because it is fairly reactive as a diene in a Diels-Alder cycloaddition. You might notice that form A also includes a diene in its structure, but form A is much less reactive in the Diels-Alder reaction. It is the special reactivity of form B that we will exploit in this lab experiment. Here is our reaction. I've copied the equilibrium from the previous slide and added a Diels-Alder. How does this work? We simply combine cycloheptatriene and maleic anhydride and heat the mixture. What happens? Cycloheptatriene is in equilibrium with its cyclohexadiene form, and the cyclohexadiene reacts as a diene with maleic anhydride, a very reactive, very electron poor dienophile, to give a Diels-Alder cycloaddition as the product shown. With a complex polycyclic structure like our product, it can be helpful to number and label atoms. Here are the diene carbons, 1, 2, 3, 4. The dienophile includes 5 and 6. These atoms in the product should be a cyclohexene, 1, 2, 3, 4, 5, 6. Let's put dots on part of the cyclopropane ring, and the anhydride is unreacted and remains an anhydride in the final product. In terms of stereochemistry, the product we will isolate is exclusively the endo product, with the electron withdrawing carbonyls being positioned closely to the alkene in the cyclohexene product. The setup for the reaction is very simple. We just combine both reagents, cycloheptatriene and maleic anhydride, together with no solvent and heat them together for about 2 hours. There are many variations for the reaction procedure. I am demonstrating the procedure from the reference in the bottom corner. Alright, so let's get started by weighing out our maleic anhydride, and we want I want just under probably 2 millimoles of this. So let's weigh this out, and that's right about 200 milligrams. Okay, so that's zeroed now. Let's see if we can get close but under 200 milligrams, like in the 190, 180 range. That's 107. It's 170. Touch a bit more. That might be too much. That's going to be too much. Just get one of those. Not enough. Okay, let's do that. Yeah, that's more than I wanted, but that's okay. That's 196 milligrams, we'll call that. Okay, so 196 milligrams. Now when we measure out the cycloheptatriene, I'll just make sure that that matches this amount. Now I'm not going to match it in terms of mass, but I'll match it in terms of millimoles, and it's going to be very close to 2 millimoles. So let's take this into the hood and get it into the reaction flask. Alright, in the hood we have everything we need to run this reaction. We have our hot plate, and our hot plate is set for 190 degrees, and keep in mind 190 degrees would be pretty hot for this reaction, but that is the surface temperature of the hot plate. Our sand bath will not reach that temperature. Now I could stick a thermometer in here and check that, but typically if you need your sand bath to be a certain temperature, you're going to have your hot plate set higher. So we have this set to 190. Now our reaction flask, I call it a reaction flask, it's really just this glorified test tube with a nice twist cap on it. And to this, I need to add our maleic anhydride. There we go. That was a little delicate because some of those pieces are pretty big, and then the mouth of that tube is not that huge. But that's our maleic anhydride. Now we need to add to our reaction flask our cycloheptatriene. So I'm going to add this as a liquid, and I need 208 microliters of this. So we'll just use a pipetter. And drip that in. There we go, and blow out the tip. Perfect. Now, I did want to weigh out the solid first, because it's pretty easy for me if I'm a little over or a little under on the solid. It's very easy for me to adjust the pipetter and get exactly the volume I need to match of the cycloheptatriene. But I am trying to keep this as close to 1-to-1 stoichiometry as possible, because that's what the reaction calls for. Now this is our complete setup. I'm not going to tighten these threads down. I'm going to keep this loose, and I'm just going to take this whole mixture, put it in the sand bath, and you could probably clamp that if you were interested, but that's pretty stable. Push that sand up around it, and we're going to let that heat. And in some procedures for this reaction, they call for refluxing cyclohexatriene. Some they just call for heating it, but that will heat. As that heats, the maleic anhydride will melt. This will become a homogeneous mixture, just a homogeneous solution, and that will heat. We'll let this heat for 2 hours. Note that because the cap is not threaded, we can release pressure as if we get gas formation and things expand in the tube. Also note that while it is very hot down here, this glassware is relatively cool. So if we do get any vapor, any boiling, it's going to come up to this cool glass and it's going to drip right back down. So this is sort of it's almost a reflux setup in its own right, with kind of an air condenser at the top. But this will be adequate for this reaction. We'll let this go for 2 hours, and we'll come back when those 2 hours have elapsed. Now this reaction has been running for about 1.5 hours, so it's getting close to being done. But I just want to show you what it looks like once it's already started. So I'm going to pull this out. I'm not sure if you can see, there is some kind of condensation liquid on the sides. That's what we hope for. So that's a sign we're getting good heating down here. And notice that everything has melted in. There is no solid in there. Everything is a nice uniform color. It's a homogeneous reaction. And that's what we want. So everything's in one phase. It's mixing. There's no solvent in this reaction. This is technically called a neat reaction when there's no solvent. So this reaction hopefully is almost complete, but we'll give it another half an hour, and then we'll stop it and we'll go to the next steps of the reaction. We have now gone for the full 2 hours, and this is still melted and still generating vapor along the sides, but this reaction should be complete. So the Diels-Alder should be done. So I'm just going to take it off the heat, leave it on the bench top, and if this reaction goes the way my previous attempts at this reaction have gone, this will solidify as this cools, and then we'll take care of the solid that forms inside this test tube. Well, after not too long, here is what we have. Now this is no longer a liquid, that is a solid. So presumably we formed our product, and our product is pure enough that as it cools, it has managed to freeze and solidify in the bottom of this vial. So the next step is to add some ethyl acetate to this. Now, strictly speaking, the procedure says get 1 milliliter of ethyl acetate, and I'm not going to get exactly 1 milliliter. I'm going to get, and I got to use 2 hands, sorry. I just can't reach what I need. Okay, here we go. And this is, that is about 1 milliliter. It's probably a little high, but that's okay. Because all we're doing with this ethyl acetate is getting this product in solution, and then we're going to add a little bit of hexane to this to precipitate it back out. And in doing so, hopefully we're going to leave behind the impurities. So I'm going to kind of scrape on this a little bit, break it up. That'll increase the surface area, but it's going to take a little time for this to go into solution. These pieces are going to dissolve, they're going to get smaller and smaller, and eventually they'll be gone. But that is the plan. So I'll need to break this up, get this into solution, and then once that's done, I'll come back and we'll transfer this actually to a different piece of glassware, and we'll end up adding some hexane and then put that on ice to let everything precipitate out. All right, now everything is dissolved, and so this is an ethyl acetate solution of our crude cycloadduct product, and I'm going to take this, I'm going to pipette this out, and it might take more than one pipette, or it may not, and transfer this into a scintillation vial. And the reason I want this in a scintillation vial is we're eventually going to form solid in here, and I'd rather form solid in here and try to filter something out of this more open vial rather than trying to fish the solid out of this long test tube. So I'm just changing the venue so it'll be easier to work with later. Now I want to take just a small, I don't want all this, but I'm going to take a little bit of ethyl acetate and squirt it. Well, I did use all of it. Squirt that down and just rinse out the sides of this. Now this is just being kind of picky and OCD, but I want to make sure all my product has been rinsed out and is now in this 20 milliliter scintillation vial. Now I don't want to use too much ethyl acetate because eventually I am going to add hexane to this. So now we're up to probably close to 2 milliliters, and the procedure technically calls for about a 3-to-1 ratio of hexane to ethyl acetate. So now if I have 2 milliliters of ethyl acetate in here, I'm going to need to use, what is that? That's 6 milliliters of hexane to get a 3-to-1 ratio. And I've just got a finite volume, so just be mindful of the volumes you're using, and if you're doing a rinse, make sure you use a rinse-sized portion, not a huge portion. Okay, now let's bring in the hexane. And so we need about 6 milliliters. I'm not going to be super careful about this 6 milliliters, but I just need a decent portion. That's about a full pipette, which is close to 2 milliliters. I'm going to drop this with, I'm not very coordinated with my left hand, so I'm going to hold the pipette with my left hand, and I'm going to gently swirl with my right this vial. I'm just going to swirl this in. So presumably what's happening is, as we add the hexane, the solvent down here becomes less and less polar, and eventually our product will precipitate out of the very nonpolar solution. So let's drip, 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 and I'm going pretty quickly, not super fast. You could also put a stir bar in here and have it stir on a stir plate as you do this. Lots of ways to get at this. I just want to mix in the hexane as I add it. Now I don't know if you can see on camera, that's just it's looking just a little bit cloudy, a little bit turbid. So my guess is in this next addition of hexane, and that was about 2 milliliters, and I'm going to add 6, so here comes approximately 2 more. Add this. I don't know if you can see the pace that's kind of the pace I'm going. Drip, 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 drip. Maybe a little faster and drip, 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 drip. Squirt it in there slowly. Again, you could swirl this. You could put it on a stir plate with a stir bar. Now that's definitely looking cloudier. And you can see in the background there's some ice. That's eventually where this is going to go. This is going to, after the hexane addition, I'm going to put this on ice. So if it's not soluble once we add all the hexane, oh, it's going to be less soluble once we cool it off on ice. Now that is definitely looking a little bit cloudy. If we could speak chemical, we might hear the chemical saying, "Oh boy, please let me precipitate." So let's put this on ice and give this a little bit of time on ice. And I think what we're going to see is some nice solid formation. So I'm going to turn off the camera just for a bit, but I wouldn't be surprised if this just takes a few minutes to see some solid. Okay, we are ready to do some filtering. Now here is our precipitated product. I'm not sure if you can see that adhering a little bit on the sides. Definitely some on the bottom. It's a little bit cloudy, so it's hard to see through and see exactly where it's solid and not. But that's cold, it's precipitated. I think it's done. It's probably been on the ice for 10 minutes or so. We have some chilled, that's 3:1 hexane ethyl acetate. So that's approximately the same composition as what we have in our scintillation vial. And we'll use that to seat our filter paper in here and also use that for the final rinse. So we want to keep everything cold. In case anything is slightly soluble, we will minimize any dissolving. You can't avoid a little extra loss because of solubility, but we just want to minimize that by keeping things cold. So I'm going to go ahead and turn on our trap and vacuum. And let's take a peek down inside this funnel and just see, yes, the filter paper, it covers up all the holes. It's important, otherwise when you try to filter, you're just going to suck your solid right through your funnel. And we will take this, and some of the solid is kind of sticking to the sides. I want to make it nice and loose, so I'm just going to break it up off the sides and off of the bottom. We'll do the best that we can. Great. And swirl it to suspend it and just dump it right on in. Beautiful. Now, you know what wasn't beautiful was I kind of did that slowly, and if you look, I did kind of a combination of pour and a combination of a decant. So a lot of my solid just stayed because this neck is a little bit constrained. That's okay. That's why we have this rinse solvent. We can use this rinse solvent. Now let's resuspend and let's pour it a little more quickly, and that'll help get things transferred. Now this isn't perfect, but it's a whole lot better than it was the first time. Do that same thing again. Get this nice and suspended and just dump it in. Perfect. Now that's not absolutely pristine, but you know what? That's good enough. Now let's take what solvent we have left in this chilled solvent, and I'm just going to squirt it around the filter paper and rinse off any residue off our product. And I think that's plenty. Now let's take the camera and peek down in there. I don't know how that contrasts, but there's a decent amount of solid here towards the right, a little bit more bare paper on the left, but that's good. That's our solid. We've collected it. Boom, there we go. Okay, so I'm just going to let this sit with the vacuum on the paper, and that's going to get a good draw through the paper. It's going to dry the product, and once that is dry and the excess hexane ethyl acetate has evaporated, we will get a mass and see what our recovery is. And here we go. Here is the final product. That compound in the middle of that weighing paper has a mass of 204 milligrams. It is a white solid. Saying something is a white solid is not very strong evidence that we obtained our product. I mean, table salt, sugar, and baking powder are also white solids, so in order to gain confidence that the reaction has worked and that our product has the correct structure, we need to examine some analytical data. That's what we'll do now. Let's discuss both the TLC and melting point data from our product, the structure of which is in the upper right corner. We also have the TLC plate from our product on the slide. There is something strange about this TLC plate. Under UV light, we see no spots. There is nothing on this plate. These faint dots at the bottom of the plate are where I spotted a solution of our product, but we can't see any dots in these lanes. In this case, we aren't seeing any spots because our product is not UV active. Spots only appear under UV light if the compound absorbs UV light. Especially in the reactions that I perform in these YouTube videos, the products often have aromatic rings to impart crystallinity in the products, so they normally give nice spots under UV light on a TLC plate. That is not the case in this product. No aromatic rings and not enough of a pi system to absorb in the UV region. We need a different visualization method to see our spots. Fortunately, there are dozens of different methods for visualizing spots. One is iodine. Here is the same TLC plate that has sat in a jar with a few iodine crystals. The iodine vapor reacts and makes brown spots wherever an iodine reactive molecule resides on the plate. For our product, the reactive functional group is likely the alkene. The spots are not terribly dark, but we can see these spots from our product on this plate after exposure to iodine. Very nice. The RF value for the spot is about 0.21, and the mobile phase was 20% ethyl acetate and 80% hexane. The important thing is that we only see one spot in each lane, which is a sign that our product is likely pure. The only difference in the three lanes is the amount of material I spotted. How about the melting point? The compound melted between 101.3 and 101.6 degrees Celsius. The literature value taken from the reaction procedure is 104. So we have good agreement with the literature value. The sharpness of the melting range is a sign of purity. The fact that our value is close to the literature value indicates we have isolated the correct product. TLC and melting point data are nice, but let's look at the NMR data. Here is the full NMR spectrum. On first glance, everything looks good. The baseline appears relatively free of extra little peaks. The spectrum was obtained in deuterated DMSO, D6 DMSO as the solvent, so we will have residual solvent peaks. DMSO itself appears around 2.5 ppm. So this signal is from DMSO. Water in DMSO, and there's always some water in DMSO, is close to 3.5 ppm. As it turns out, the middle signal in this group is from H2O. I always like to see a full wide view of a spectrum, even if there are no peaks in much of the full spectrum. It's important that there are no peaks way downfield because our product should not have any peaks here. With this product being an anhydride, it is possible that it could react with water and form two carboxylic acids. If that happened, we would expect to see carboxylic acid signals, the OH acid groups, way downfield. We do not see those signals, so that's a good sign that our product has not hydrolyzed. Okay, let's zoom into this spectrum. Here is a bit closer look with just the action region. Again, two of our signals are from our NMR solvent. Always keep track of your NMR solvent peaks so that you do not try to interpret these signals as part of your product. Here is the downfield region with integrations. The most downfield signals should be the alkene CHs between 5 and 6 ppm. We have a 2-hydrogen signal at about 5.9 ppm. It looks a bit like a triplet. That's interesting because the alkene hydrogens have only one neighbor. To get a triplet, we would need some long-range non-vicinal coupling. That is possible in rigid ring systems like this one. We have two two hydrogen signals between 3 and 3.5 ppm. I don't know which is which, but one of these signals is from the hydrogens next to the carbonyls, and the other is from the bridgehead hydrogens. Both are somewhat broad and would be singlets. Don't forget to ignore the water peak. And here is the upfield region. These are all signals off of the cyclopropane ring. The 2H signal includes the two CH groups, which are identical by symmetry. The two individual 1H signals are from the different CH2 hydrogens. Normally, when you see a CH2, you think of a two hydrogen singlet or some kind of two hydrogen signal. In this case, the two hydrogens are not magnetically equivalent. They have different electronic environments and therefore have different chemical shifts. One is at about 0.3 ppm and the other is at about 0 ppm. Both are some form of a quartet. With a clean NMR spectrum, a single spot TLC, and a sharp, reasonable melting point, the product looks good. Let's determine the yield. All right, here is the reaction again. Let's first identify the limiting reagent. For cycloheptatriene, we used 208 microliters with a density of 0.888 grams per mole. We have a mass of 184.7 milligrams. Based on a molecular weight of 92.14 grams per mole, we used 2.00 millimoles of cycloheptatriene. Okay, for maleic anhydride, we used 196 milligrams. Based on a molecular weight of 98.06 grams per mole, we used 2.00 millimoles of maleic anhydride. Great. Since these two reagents react in a 1-to-1 ratio, we wanted to use them in a 1-to-1 ratio in the reaction. We did. 2 millimoles of each. Both reagents are equally limiting, and 2.0 millimoles is our theoretical yield. What is our actual yield? We obtained 204 milligrams of product based on a molecular weight of 190.20 grams per mole. We obtained 1.07 millimoles of product. That is our actual yield in millimoles. So our yield is actual over theoretical times 100 to give a 54% yield. Wonderful. I admit that our reaction reference got a yield of about 90%. There are probably two reasons for that. One, they ran the reaction on a larger scale. Larger scale reactions sometimes allow for the minimization of product loss. Two, they had a more involved product isolation process. In simplifying the isolation, I sacrificed some yield. Regardless, around 50% is good enough for use to make a useful amount of material. Furthermore, the product looks very clean based on the NMR, TLC, and melting point data. I hope you enjoyed seeing this example of a Diels-Alder reaction with a fluctional molecule, cycloheptatriene, as the diene. If you are interested, handouts for the procedure are linked through the video description. Please subscribe, like, or leave a comment. Take care.